All right, so we're going to look at some applications of application problems with Extrema in multivariable functions. So the types of problems that you might be asked to solve with the tools that we've been using. So let's look at this. I like this type of problem. I think it's interesting, and it makes you think in a three-dimensional way. So we have a function z equals x squared plus y squared, and we want to find, and we have a point 5, 5, 0. So we have a point on the xy plane. We want to find the minimum distance from the point to the surface. They're installing solar panels on the roof.
Oh, right.
Mm-hmm. So we want to find the minimum distance from this point to surface. So first off, let's do a quick sketch. What kind of surface is this? Cone?
With straight edges.
Parabolic.
Right. So cones have flat sides. So this would be a
It's a cone.
paraboloid, right? If we look in the xz plane, z equals x squared, we get a parabola. In the yz plane, we get z equals y squared parabola. For z constant, we get circles. So we get this paraboloid.
Is it only in the positive x there? It doesn't drop down to the negative?
Right, because x squared and y squared are always positive, so z always has to be positive. And then we have this point out here on the xy plane, 5, 5, 0, and we want to minimize this distance from the point to the surface. So how are we going to do that? Let's call this point on the surface x0, y0, z0. That's the point on the surface where we have the minimum distance. So how are we going to go about minimizing this distance? How do we express the distance from this point to the paraboloid?
No, x sub 0 minus 5 root x 0 minus 5 squared.
There we go. So the distance is the square root of x sub 0 minus 5 squared plus y sub 0 minus 5 squared plus z sub 0 minus 0 squared, right? On the surface, we don't want to know what this point is. So on the surface, we can write x0, y0, z0. How can we express x0, y0, z0 in terms of what we know about the surface? What if we call x0 x? What would y0 be? Y. And how about z, 0? On our surface. X squared plus y squared. Because on the surface, z equals x squared plus y squared. So those are our points. So let's plug those into our distance. So our distance is x minus 5 squared plus y minus 5 squared plus x squared plus y squared squared. And we want to minimize this distance. Now, to make our calculations a little easier, we're going to say that the distance is minimized when just what's inside the radical is minimized. So we're not going to worry about the square root. So we're minimizing the square of the distance, and that's going to minimize the distance. So we're just going to worry about this part. So we want to minimize x minus 5 squared plus y minus 5 squared plus x squared plus y squared squared. So to minimize this, what do we need to do? We need to find our critical points. We need to find our first partials, figure out where they're 0 simultaneously, and find our x, y's, and z's. So let's find our critical points. I'm going to switch pages, but we're minimizing this quantity. So our first partials, so we're going to minimize, I'll call d, capital D, our distance squared. So d sub x is, when I simplify this, I'm not going to go through all the steps. The first partial is 2x minus 10 plus 4x times x squared plus y squared. And the partial of our distance squared with respect to y is 2y minus 10 plus 4y times x squared plus y squared. And we're looking for our critical points. So we're setting each of these, we want to figure out where each of these is 0. So I'm going to simplify these a little more. I'm going to write dx is 2x minus 10 plus 4x to the third plus 4xy squared. And dy is 2y minus 10 plus 4y to the third plus 4x squared y. And we want each of these, we're going to minimize our distance squared. We're looking for our critical points, so we're going to set each of these equal to 0. And we want to find, in order to find our critical points. So we want dx equal dy equal to 0. So I'm going to set each of these to 0, and we need to solve some simultaneous equations. So when we set these equal to 0, I'm just going to divide out, because each one has a factor of 2. I'm going to get rid of that factor of 2, and we come up with 2 equations. Our first equation is going to be x plus 2x to the third plus 2xy squared equals 5. And our second equation is y plus 2y to the third plus 2x squared y equals 5. And we need to solve these two equations. So how are we going to go about solving this system of equations? Anybody have an idea? What's that? Set them equal to each other. We could do it that way. I think there's an easier way. I'm going to multiply 1 by y, multiply 2 by x, and subtract. If I multiply 1 by y and 2 by x, we end up with all the same terms, except we have a 5y here and a 5x here. When I subtract those, I get 5y minus 5x equals 0. Or that tells me that y equals x. So these are 0 when y equals x. Now I'm going to substitute into equation 1. I'm going to substitute x for y in 1. So that gives me, in equation 1, when I make that substitution, I get x plus 2x to the third plus 2x to the third equals 5, or x plus 4x to the third equals 5. Now, how do we solve this? And I don't have an x squared, I just have an x. So Scott says factor, so let's say, or we just factor in an x. Like so. Any ideas? What do we come up with? So we have this cubic equation. What if we were given this problem on a test? How would you go about solving this cubic? What are some methods you could use? Graph it. See where x plus 4x to the third intersects the line y equals 5. So you could look for the intersection. This problem is kind of nice because if you were clever, you would look at this and say x equals 1. X equals 1 works in this equation. So we could say by inspection x equals 1. What's that? By inspection, right. Guess and check by inspection, kind of the same thing. Or we could graph it. We could use the methods. We could figure out the factors, synthetic division, stuff that you learned in Algebra 2 to figure out the roots. Or if you knew the general form of the solution to a cubic equation, you could use that. But this one's nice, we can figure out x equals 1. So if x equals 1, I'm going to substitute x equals 1 into my equation here, into 1. Substitute into equation 1 and solve for y. That tells me that y equals, we end up with y equals plus or minus 1 when we substitute in here. And we need to check in equation 2. Check in equation 2 to see that equation 2 is only true when y equals positive 1. So we have x equals 1, y equals 1, and from our original equation, z equals x squared plus y squared, z has to be 2. And our minimum distance, we can plug into our distance formula, and we find that our minimum distance turns out to be 6 units. So plugging in x equals 1, y equals 1, and z equals 2 into our equation for the distance, we find our distance is 6. So this is an example of the type of problem you might be asked to do with a maximum, in terms of a maximum minimum application. Questions on that one? All right, let's look at another example. We want 3 positive integers x, y, and z such that x plus y plus z equals 32. And x, y squared, z is maximized. So we're going to go through this one with the methods that we've learned so far. On Monday we'll talk about a different method of solving this. So we're looking at a function that we're trying to maximize, and we have a constraint. So we're going to work with it one way today and a different way on Monday. So from this equation, we know that z equals 32 minus x minus y. And we're going to say our function that we're looking at, we want to express this just in terms of 2 variables. So f of x, y, z is x, y squared times 32 minus x minus y. And if I expand that out, I can write that as 32xy squared minus x cubed y squared minus xy cubed. X squared. So this is the function that we're trying to maximize. So we want to examine this for critical points. So we need to take our first partials. So f sub x, the first partial with respect to x, is 32 y squared minus 2xy squared minus y to the third. And we want that equal to 0. We're looking for critical points. F sub y is 64xy minus 2x squared y minus 3xy squared. And that equals 0. So this is where we find our critical points. So let's look at the first equation first. We want to solve that. Figure out where this is 0, and then we'll look at the second one. So for the first one, we're going to factor out. I'm going to factor out a y squared. So I'll have y squared times 32 minus 2x minus y equals 0. So one possibility here is that y equals 0. But we want non-zero integers. If x equals 0 and y equals 0, our problem is not as interesting. So we're going to ignore y equals 0.
Wait, would it still be right? Is 0 considered a positive integer?
No, 0 is not a positive integer. 0 is not positive or negative. So we're looking at 32 minus 2x minus y equals 0. So y equals, I'm just going to solve this for y. y equals 32 minus 2x. Now we're going to look at number 2 and work with this one. So we're going to say that I'm going to factor out a y out of this one. So y times 64x minus 2x squared minus 3xy equals 0. Again, we're going to ignore y equals 0. We don't want y equal to 0. So we're looking at where 64x minus 2x squared minus 3xy equals 0. We can what's that? I'm just going to, what I did, we could multiply the first one by x. I just substituted this in for y into this one. So this is just the method that I chose to solve this one. So I get 64x minus 2x squared minus 3x times 32 minus 2x equals 0. If I simplify this, I end up with 4x times x minus 8 equals 0 after I simplify and factor. So we're going to ignore the possibility that x equals 0. So x equals 8. We can use this equation now to solve for y. So we plug this 8 in for x here. So y equals 16. And z then has to be 8 for these two to add up to 32. So we've come up with 3 positive integers such that their sum is 32 and their product x, y squared, z is maximized. And on Monday we'll look at a different way to go about this one. So the downside of maximum minimum problems is they often involve a lot of algebra. The upside is we can find maximum minima of some interesting things. So questions before I talk about something that's kind of tangentially related? No questions? What's the derivative of this subject? My tangent has to do with least squares line. So we've all worked with, in your calculator, you can put in a set of data and calculate the linear regression very easily. Your TA84 can do that. Have you all done problems that involve linear regression line? Yeah. So what's interesting is that we have the tools to talk about where the least squares regression line comes from. We're not going to go through it, but I want to show you that what we've talked about today leads us to the least squares regression line. So we have a set of points, and I'm just going to draw a graph here. Here are my axes, and we have a set of data points, x1, y1. And up here we have x2, y2. And over here, down here, we have x3, y3. And we're going to keep going. We have a bunch of points. These are just our first 3. And we want to fit a line to this data. So we're constructing a line that fits this data as best we can. One way to do this is we look at the vertical distance from the line to each of these points. And I'm going to call this distance, this vertical distance, D1, D2, D3. So we have these distances from the point to the line, and this line has some equation, y equals f of x. So one way that we minimize the distance from the points to fit our line to this data is, like we just did in our example, we minimize the square of each of these vertical distances. So we want to minimize we're going to call it S, is the sum, we're adding all these distances together, I equals 1 to n, for however many data points we have, of f of xi minus yi. So we're minimizing the distance from this point that's on our line, the vertical distance, to our data point. So we're minimizing the sum of these distances, we're minimizing the square. So we're minimizing the sum of those distances squared. And our line, our f of x, is some line ax plus b. So we have a slope and we have an intercept. So the sum is a function of a and b. So this sum is a two-variable function. And we're minimizing this quantity. So what we've just talked about, the tools that we've just talked about, allow us to minimize this quantity. We can use the tools that we've just been using. We can find the first partials of this function with respect to a and b, because this function this function that we're minimizing is going to be a function of a and b. We can take the first partials with respect to a and b, set them equal to 0, use our second partials test to show that we're at a minimum, to find a and b such that this is minimized. Now I'm not going to go through it because it's really long and difficult, but I want to show you the results just to kind of make a point here. So when we go through this, we can use, we have the ability, we have the knowledge now to minimize this distance using the tools that we've talked about with our finding our critical points and with our second partials test. We come out with, when we do this, go through this process, A is n times the sum from I equals 1 to n of x sub I, y sub I, minus sum I equals 1 to n, x sub I, sum I equals 1 to n, y sub I, all over n sum I equals 1 to n, x sub I squared, minus so this, when we go through our finding our critical points using our second partials test, this is what A equals, and B comes out to be 1 over n times the sum I equals 1 to n of y sub I minus A sum I equals 1 to n, whoops, of x sub I. So to count, and y equals our line, ax plus b is the least squares line. So using the tools that we've just developed, we could go through this process to calculate a least squares line. Now, just looking at the form of this, think how difficult that would be to calculate by hand. finding those partial derivatives, setting them equal to 0, finding A, finding B, all these sums. So one of my points here is that our calculators are pretty amazing, that they do something like this for us. So in Algebra 1, we can calculate a least squares line without even really thinking about it. So I think it's pretty cool that we've come to a place after a semester and a month or so in calculus where we have the ability to do this. We have the tools to come up with this, to verify the form of this procedure that we've always kind of just taken for granted because it was easy to do on our calculator. My second point is that this kind of points out that calculators are actually better than thin mints.
No.
And
Disagree.
This equation would have helped you live if you were starting today.
That's true.
it's arguable whether thin mints would either. So,
Oh, they would.
so anyway, my point here is that we've developed these tools, and the problems that we do may seem kind of, they tend to be kind of contrived, but we have developed a very powerful set of tools that when we're applied in a certain way, we can come up with very powerful results like the least squares regression line. Any questions? All right, homework. All right, there you go.